streaming, not screaming, hopefully. Not yet, anyway. And we'll pick up in Lecture 2 then, which will give us a chance to review some of the terminology and such from this morning. So we talked earlier briefly about the idea of modeling change versus fluctuation. Multi-level models are suited to both of these types of longitudinal data, but what you put in the model is going to be dictated by which kind you have, and there are places in the middle as well. So in terms of the model for the means, the fixed effects, our goal is always to describe what happens on average. So in the context of within-person change, we're trying to describe the average trajectory. In the context of within-person fluctuation, these kinds of studies over here, you may not need any effects of time whatsoever in the model for the means. So this picture here depicts flat lines across time. It's not that stress or affect or whatever this is systematically increasing or decreasing. It's just that it fluctuates. So there would be nothing for an effective time to do in this model. It wouldn't help as a predictor. That being said, you do need to think about unexpected effects of time in these sorts of designs, such as day-of-the-week effects, reactivity effects, time-of-day effects. If you're measuring something like cortisol across the day or fatigue across the day, those things fluctuate in normative patterns, and time would be in that context instead. In terms of the model for the variance then, in the context of measuring fluctuation, or change, this is where we're headed this afternoon, our goal is to describe which of those fixed effects needs random variation around it. Which growth model term do people need their own of? In doing so, what we're doing behind the scenes is allowing the pattern of variance and covariance across time to look more like what it would be in the data, non-constant in most of these cases. In the context of within-person fluctuation, random effects of time still aren't going to help you. If you don't have a line, odds are good that people don't need their own version of it. But what you do need is still to think about any potential reasons why variance would be different across time, time-of-day effects, day-of-the-week effects, and so forth. And if not, just make sure that you're covering the right pattern of covariance. Occasions that are closer together in time are likely more related, and there are covariance structures that build that in, such as autoregressive topolits and that kind of stuff. That's Chapter 4 of the book. I'm not going to get a chance to talk too much about that today, but I'm happy to answer more questions about that as well. So in terms of the model for the means, what kind of change are we expecting? And so far, we have talked about, I have talked about, you have listened about, two different kinds, empty or saturated. So empty says no change. There is only a fixed intercept in an empty means model, whereas saturated means as many parameters as you have occasions. So as many means as you have occasions. This is only possible in balanced data. If you try to fit a saturated model to unbalanced data, you would be asking it to come up for a separate mean for every single possible time value, which may not be useful. What you can do in this case is just to get a sense of what the mean trajectory looks like is to round time into some kind of convenient interval just to make a picture. Not to put it in a model, but just to make a picture, because it's helpful to know where you're going in order to get there. So what we do in the middle here is try to do some kind of trajectory that approximates the saturated means decently well, but does so in a way that's going to make more sense for interpreting change over time and hypotheses about differences in change. So polynomial models is what we'll have time to look at. I'll be able to show a couple brief examples of piecewise slopes, and nonlinear slopes would be other options as well. So the idea is to characterize the function that created the means, not just to replicate the means in and of themselves. On the variance side, same idea, but with respect to pattern of variance and covariance. So here are the two variants of repeated measures ANOVA. The univariate version on the left here, let me get my happy little pointer, laser pointer. This is compound symmetry. This is random intercept only. This is everybody changes the same. People only need their own mean, and you're good to go. So this model has two parameters in its variance model, no matter how many occasions there are. you have E variance at level 1, which is within person's residual, or random intercept variance at level 2, which is between person mean differences. You estimate one variance at level 1, one variance at level 2. That variance at level 2 is what creates the covariances. So this thing has only two parameters, regardless of whether you have 2 occasions or 80. On the other side is the most complicated model that you can fit. It's the answer key. It is right. It is just spitting the data back out. It has as many variances as you have occasions and all possible covariances for all possible pairs. So this has 10 parameters for 4 occasions, would have 15 for 5, and so on. This is only possible in balanced data, whereas compound symmetry is always possible. So we're looking for something in between, some kind of structure, some kind of pattern that does as good as unstructured, or not worse, really, but uses fewer parameters to do so. And so we'll look at options that are more common in models of change, random effects, as a way of approximating this middle structure right here. So here's the picture that we had from this morning. This is an empty means between person and within person split 2-pile model. So the difference between the grand mean and each person's mean is carried by their U0I, their random intercept. The variance across persons in that U0I is my level 2 random intercept variance. It captures between person differences that are cross-sectional, that are inter. And then from there, E is the difference between the person's mean and each individual occasion's outcome. That's within person's level 1 residual variance. That's the longitudinal part. That's the intra part. Now let's see that same idea using the notation of multi-level modeling. So everything that I've shown you in Lecture 1 was composite model, where it was just written as one equation. I'm switching that up to use placeholders to describe it as a multi-level model. So this is just a way of writing a model. It doesn't change what's in the model, it changes how it's described. And when you only have an empty random intercept model like this, it looks like overkill. But it quickly starts to become useful to keep track of what is going on in each part of the model to have it broken out into this way. So we had an empty model that's one pile of variance up here this morning. So y for each individual is a function of a fixed intercept that was beta 0 that everybody gets in the model for the means. And EI is how far off your occasion is from that fixed intercept. So in switching the model and its notation to become a multi-level model with 2 piles of variance, we make several switches here. First off, yi goes to yti. You saw that earlier. Second, ei goes to eti for the same reason. So it's per time, per individual. And now beta 0 picks up an I. Beta 0 is in black here on purpose because beta 0 is not a thing. By thing, I mean estimated parameter. It is a placeholder for estimated things. So beta 0I is a representation that indicates how each person's intercept is to be created. It's an idea. That idea is then defined more specifically in its own equation at level 2. So beta 0I is how each person gets their own intercept. It starts off with a fixed intercept. And I'm switching notation here to go with the book and with almost everyone else's that I've seen in books. This Y-looking thing, that's a gamma. In different fonts, it looks more or less like a Y and sometimes like a V, but that's a gamma. So gamma is now my new term for a fixed effect, that everybody gets the same. So it has a 0, 0 here, no I. Each person has the same gamma 0, 0. The zeros refer to its order in the equations at level 1 and level 2. So if you think about the intercept as the jumping off point for any equation, the first 0 here is 0 because we're talking about what goes into beta 0 at level 1. The second 0 is that it's the first term in predicting beta 0. It's the jumping off point for beta 0. Then we pick up U0I, which is the same as before. That's my random intercept. So what the intercept is on average is the fixed intercept here in red. How far off mine is in blue. So if I'm doing better than everyone else, U is positive. If I'm doing less well, it's negative. And then those two get put back together to come down to level 1 and pick up the E. So the composite notation is down here in the right-hand corner, in which we've just swapped out the term in parentheses for the beta 0. So this term has 3 parameters: 1 fixed intercept, 1 level 1 E residual variance that's within persons, 1 level 2 random intercept variance that is between persons. And when you are doing multi-level modeling, this is always first, because step 1 is to figure out how much of your data is actually longitudinal. Do you in fact have a longitudinal sample? So before break we looked at intraclass correlation. Remember that? It's level 2 over level 2 plus level 1. It's between over between plus within. It's random intercept over random intercept plus residual. So it can range from 0 to 1. If it is 1, what happens? No within. Game over. Do not pass go. Do not collect $200. You do not have longitudinal data. And I have seen this happen. The second time I got to teach this course at Penn State, I had a student, and back then I used to let the students analyze their own data for homework. And this was homework 1. Make a spaghetti plot of individual trajectories and calculate an intraclass correlation. And this student came back with an intraclass correlation that was like 0.9999999, and a plot of the most perfectly flat lines in parallel that I have ever seen. And I had to sit him down and say, dude, and he's like, no, I'm going to be the first person in my field to do a longitudinal study. I'm like, dude, no, you're not. You do not have longitudinal data. And he dropped the course, and I don't know what happened. And I felt bad for a few minutes, but then I thought, wait a minute, we're having this conversation at the end of January, not during his final defense, when he's trying to explain why he couldn't find any within-person effects. So step 1, find out if your data are in fact longitudinal. Anything below 1, you're good. Now what if it's 0? Could that happen? It can. It can be all within with no between, but what's going to happen is that the between will start to increase when you explain the within. So it won't stay 0 for long. That can happen if you're studying a phenomenon that's fairly normative. There's an example in, I think, the Hawks textbook looking at a number of words that toddlers know, and they start at 12 months where all the babies know 1 word. So there's no between variation, but as they grow, they spread out. So if you don't have time in the model, it might look like the babies are all the same, but that's because the model's not complete yet. So ICC of 0, play ball. ICC of 1, go home. That means you can either average across occasions or just use 1 occasion, but functionally speaking, you have cross-sectional data. So this is always step 1 for that reason. So then in thinking about change, we'll talk about time. So in your heads, I want you to think about how this applies to your own data. Growth curve modeling folks, raise your hands. Who's looking at change over time where they're supposed to change and that's the whole point? Okay, for you, time is time. Time is the thing that you carefully selected because it was far apart in time that you would actually see some change, and that's the thing you care about. Fluctuation, EMA, Palm Pilot people, the rest of you? Yeah, so for you, it's not time in study. Think of it as like day of the week or time of day or something that is related to time but not necessarily the point. It might be something you have to control for. But these same techniques work in both of those situations. The difference is the amount of weight you give them an interpretation. For within-person growth modeling people, this is the point. For fluctuation people, this is the thing I have to do first so I can get to the stuff I care about. But in either case, we can talk about time as having 2 possible effects. Is there an effect of time on average? And I just realized we have a lovely typo here. Is the fixed line describing the sample means not flat? There we go, that's better. If so, you have a significant fixed effect of time. That's the part that ANOVA can tell you just fine so long as you have balanced data. The more interesting question then, from my perspective, And the question you can only ask if you have 3 or more occasions per person is, does the average effective time vary over individuals? If so, you need a random effective time too. And you can have both fixed and random, neither fixed nor random, or any combination thereof be significant in your model. So here's some pictures. Each of these pictures has a random intercept, so we're focusing entirely on the slope. So in these pictures, the x-axis is time, the y-axis is whatever your outcome is, the heavy black line is the sample mean line, and these are individual trajectories. And I didn't draw the little dots around the trajectories. These are like best fit lines for each person's data. So picture A here in the top left shows no fixed effective time, no random. There's no fixed effect because on average there is no effective time. The average line is flat. There's no random effective time either because that flat line works equally well for everyone. Everybody, no changes, the same. That's how my son Huey would say it. We no change the same, Mommy. He's 3, so I give him a pass on the grammar. So no fixed effective time because on average this sample mean line is flat. No random because the flat line works equally well for everybody. Next one. Yes, there's a fixed effective time, no random effective time. Now the average line does have a slope to it. On average, people are growing in this outcome over time. But people are growing the same. People don't need their own slope, so there's no random effective time. These are the only 2 situations in which the univariate approach to repeated measures ANOVA would likely be okay. Both of these patterns show compound symmetry, show random intercept only, show equal variance across time, and likely equal covariance as well. Here's the most interesting case. Let's say that you're doing a model of change for your dissertation. It takes you 2 years to collect data. Just hypothetical, right? You shouldn't nod that hard. She's like, yes, that's what I'm doing. And after 2 years of data collection, you throw your model into an ANOVA, and you find there's no main effective time. Wah, wah. And you might go home and cry, and that would be okay, but you should come back and make a picture. Because if your picture looks something like this, this indicates that you've missed the story. On average, there's no effective time. The average line is indeed flat, but that's because some people grow and some people decline. So we do have a random effective time in this picture. And if this was, say, a treatment study where some people got better and some people got worse, you might want to know who you hurt instead of helped. I'm playing clinical psychologist today. So yes, the fact that there are random effects of time are more interesting, and so you'd want to figure out what it is that differentiates the people who declined from the people who improved, or the people who improved more from the people who improved less. And last but not least, you can have both. So on average, yes, people are improving, but people improve to different extents. So this possibility of having all combinations here dictates that even if there's no significant fixed effective time, you are indeed allowed to continue to test whether or not there's a random effect. You would leave the fixed effective time in the model when doing so, though, even if it's not significant. Because as we'll see here shortly, the random effects of time are phrased as deviations. They're going to be how far off from the fixed effective time your slope is. So you need what it's off from to be in the model for that to make sense. What it's off from is the fixed effective time. So that stays even if it is functionally 0. And we will use different ways of assessing significance because these are different sides of the model. A fixed slope, we can just stare at the p-value on the output that shows up next to it. By the way, that is called a walled test. If you don't want to write, we stared at the p-value in your manuscript. Random slopes, then, we're going to do likelihood ratio tests because that's a model for the variance parameter. And the reason for the difference is that fixed effects are unbounded. they have a null hypothesis of 0, and they can be either positive or negative to infinity. So a typical significance test based on a two-sided sampling distribution, which is what the Wald test is, makes sense. Random effects can't be negative. So you can't stare at a Wald test for a random effect, even if it shows up on the output, because there's no negative half for the sampling distribution to occupy. So we have to do something different, and that's a -2 log likelihood difference. Okay. Questions on that? So fixed is what everybody shares. Random means you need your own. So here is a model that would go with the B slide here. So just to orient you, this first model here, empty means random intercept, that would predict the A column here. An empty means model, no random slope. So I have a fixed intercept and a random intercept variation. So that model predicts this pattern. The next model we'll look at would predict this pattern in B, which is fixed linear time random intercept. And I'm starting with linear because linear is easy. These can be nonlinear too. We'll get there. So fixed linear time, comma, random intercept. I am using those words to clearly delineate which terms are included on which side of the model. Fixed on the mean side, fixed time on the mean side, only a random intercept on the variance side. All models have a residual variance, so you don't have to talk about that. That's a given. So then expanding our multi-level model notation, still y at each time for each individual equals how each individual gets their own intercept beta 0. That's the same as before, but now we've picked up beta 1I, which is how each individual gets their own linear time slope. Time gets a ti subscript because in theory you could have a different set of times for every individual. So time is a time-varying predictor. So any variable that shows up at level 1 here gets a ti. Y is a variable that gets a ti, time is a variable that gets a ti, E is a variable that gets a ti. Because there are 2 beta placeholders at level 1, there are 2 beta equations at level 2. There are as many level 2 equations as you have beta placeholders at level 1, always. Now this is going to be overkill in this sense because beta 1 is nothing but a placeholder for a single fixed effect. Gamma 1 O. That's my fixed slope. So everybody shares this same slope, which is the change in y per unit change in x. So you can think about it per unit time. I would encourage you never to write that in a results section. Unit time is lazy. No, it is. It's per day, it's per month, per semester, per year. You know what your unit is. Don't make your reader figure it out. That's my philosophy. These models are hard enough as it is. So unit time is my generic language. I would always substitute that in for what time is in your study. So the combined equation then looks like this down below, where the time variable is only multiplied by this single term, creating the same slope for everybody. Because of the change in adding the fixed linear time slope, the fixed intercept changes its interpretation. The intercept is always the expected outcome when the predictors are 0. Before we had no predictors, so it was the grand mean. Now it is the intercept specifically at time 0. And that is also something that you should tell your readers. You can tell them at the beginning, we centered time such that 0 was the first occasion, or we centered time such that 0 was age 5, or sophomore year, or whatever it is. So then you can talk about the fixed intercept as the expected y for at baseline or at age 5. So you can fill in intercept to make it sound like it's more meaningful, because it is. E then is why are you off your line? It's the idea that after controlling for a fixed effective time, the line does not describe each person's data perfectly, and so you still have these residuals. And we assume that the E variance is constant across occasions and persons, although both of those are testable assumptions. Okay. Questions? Or any of that you want to hear again? Now, a few little complications here. Significance for fixed effects is easy. You stare at the p-value. That's your wald test. Effect size in MLM is much trickier. There is no one universal accepted standard for effect size. You can convert summary statistics to other effect sizes, like there's formulas you can convert T's and F's into D's and stuff like that. You can still do that. What is often common here is a measure called Pseudo R Square in MLM. And this is not me being funny. That's what it's called. Like, everyone calls it that. It's Pseudo R Squared because it can behave squirrely. It's supposed to be variance accounted for by predictors, but in models that have more than one pile of variance, there's more than one possible Pseudo R Square. So to the extent that time is purely within persons, that's how we think about it in most designs, because time is a level 1 predictor, let me back up here, time goes in at level 1, so logically it should explain the variance that's part of its own equation. It explains level 1 E residual variance here. So we can calculate how much variance we have accounted for relative to what we started with. So the generic formula for Pseudo R Square here is the variance component from the model with fewer parameters minus the variance component from the model with more divided by the variance component from fewer. So if we start with an empty means, let me go back up here. If we start with this model right here, how much residual variance do we have before we do anything? After we made our two piles, we keep the piles the same, we add fixed time. Now how much variance did we account for? So it's what it was minus what it is over what it was. And we can talk about the reduction in the residual variance specifically. And specifically is important. Because if I have, let's say, let me make some easy math here. If I have an intraclass correlation of 0.9, an intraclass correlation from an empty model of 0.9 means it's 90% between, 10% within. If I then have a Pseudo R Square after accounting for fixed time of 50%, doesn't that sound impressive? Have you ever seen an R Square of 50% in your life? In real data? No? In simulated data, sure. However, it sounds much less impressive when you phrase it as, of the 10% that was within persons, we got 50% of that 10%. Or what most people would call 5. So it would be disingenuous to say that you had an R square of 50%. It would be accurate to say, I have a Pseudo R Square for the residual variance of 50%. That is accurate. And in an ideal world, that would be where the story ends. However, to the extent that time varies between persons, you have to worry about what happens at level 2. And this is an advanced topic that shows up in Chapter 10. This happens in accelerated longitudinal designs, or whenever you have a design in which people start out at a different point in time. So this is common in educational studies where you might have like 3rd, 4th, 5th graders and you follow them each for 4 years, that kind of thing. In that case, the difference between being a 3rd grader, a 4th grader, or a 5th grader when you start, that's between person variance and grade. To the extent that that matters, it will capture random intercept variance because grade is a between-person predictor and a within-person predictor. So if you have between-person variance in time, you would also want to report a Pseudo R Square for the random intercept. And you would actually need to have 2 different parameters in the model for each type of effective grade. The effect of starting out older and the effect of getting older as 2 separate model parameters. That way you're not ending up smushing the 2 together into one term. But if time is purely within persons, which is the case if everybody has the same occasions and everybody starts out at the same place, then what's going to happen at level 2 is counterintuitive. You would think that level 2 stays the same. If time is purely level 1 within persons, it should explain purely level 1 residual variance, and level 2 should be fine. But what's going to happen is that level 2 variance is going to go up. And I want to explain why this happens so that you're not freaked out when you see it and think you did something wrong, because you didn't. The way that these programs, all of them that use maximum likelihood or residual maximum likelihood, try to identify how much is true between person variance is after correcting it for how much they think is attributable to chance. So if I divided this room into 10 random groups, and I asked you to calculate, say, the mean height of each group, would each group have exactly numerically the same mean height? Probably not. You'd see a little bit of variation just from the random pairing of people, right? So that's what it's trying to correct for, is how much of that between is just chance, is just random noise. And the way that it approximates what random noise is as the level 1 residual variance divided by the level 1 number of observations per level 2 unit. This term right here, let me get my pointer back, sorry. It doesn't understand that I'd like the laser pointer all day long. So yes, so we have what is true, and it takes this thing and creates observed by getting rid of it. So true is observed minus that. So true is what shows up on your output. It's already been fixed for you. But the problem is that the fix changes as the models change. So for example, these are numbers that show up in the first part of Chapter 5. If I have an observed level 2 random intercept variance, so if I have perfectly balanced data, I output the person's means. And I look at the variance of those person's means, this is what I get, 4.65. If I also have a residual variance at level 1 of 7.06, and I have 4 occasions per person, what SAS is going to do is go, oh, okay, well, here's what the observed variance is. Here's my correction factor based on the amount of residual variance, and here's what I think your between-person random intercept variance should actually be, 2.88. If you then add a fixed linear time slope, that should reduce the level 1 residual variance, and it does in this example from 7 to about 2, which is a pseudo R square for the residual of about 70%. Now we start out with the same amount of level 2 observed person mean variance, but the correction factor has shrunk because there's less residual variance to correct with. So now it looks like what SAS thinks the true between person random intercept variance is 4 relative to 2. So it's kind of screwy, but it happens. And this is why even with an intraclass correlation of 0 and an empty model, it's going to come back. It's going to come back higher the second you start explaining residual variance at level 1. So they're yoked together in this way, which means that whenever you explain just level 1, level 2 random intercept goes up. The piles of variance can also shift around as you add terms to your models, particularly in unbalanced data, and so sometimes they go up for that reason. I've seen them go up if you add a predictor that's truly non-significant, that's really just noise. It will make the variance worse instead of better. And so that's why these are called pseudo R squares, is because people just sort of accept, yeah, they're a little screwy. And more often than not, they behave that way. But this is one instance in which there really is a reason, and so I wanted you to know what it was. Gentleman in the purple. Yeah. Power for what? Power for multi-level models where your simple true variance or your effect size are bouncing around. You feel like if you are doing something in level 1, level 2 is going to change the parameters of doing the power analysis on it and bounce around, not immediately obvious in a good way. I would use the intraclass correlation that you end up with in the model that you're trying to power. And I would use that combined with your level 1 sample size to compute what is known as an effective sample size. It uses a design effect that essentially corrects your sample size for the effect of the clustering. And if you use the intraclass correlation from the model you're trying to power, that should be the relevant one, not the one from the empty model that you're not trying to power. The first part of Chapter 13 has some examples of how to do that. And I also talk about that in my brief unit on clustered data in the advanced class. Yeah, I do it backwards. I know there's some folks who teach MLM for clustered data and they have a week on longitudinal. I teach 2 semesters of longitudinal with a week on clustered. But once you get time down, clustered data is relatively simple from my point of view. And I'm sure they'd say the same about going the other way. But it shows up in that unit because oftentimes people are interested in people. They just happen to get them from groups. And so they have to figure out how much more people they need because they're from groups. And that kind of correction for interclass correlation and design effect is much more relevant in that case. But that's what I do. Right. Other questions? So, yeah, please. It depends on what the meta-analysis was about, but in theory, if they have the pseudo R square, they should have had the variance components they computed it from, and those might be useful in their original state, because the pseudo R square value depends on how much there was to begin with. So if they're willing to provide it, I would get that. But usually, it's fixed effects are what people do meta-analyses on, not so much random effects, and so I'm not sure if that would be as relevant in that case. Others? Yes?
In your earlier example, I think you said the grade was like both between and within.
Mm-hmm.
Could you explain that just a little bit? I didn't quite get it. Like, is it like comparing fourth graders of this year to last year's fourth graders?
Yeah. So whenever you have a design, it's called an accelerated design or an overlapping cohort design or sequential cohort design. They go by lots of names. And it's the idea that you want to measure longitudinal change over a wider span than you're ever going to get in your life. And so you cheat. So like if you have 3rd, 4th, 5th graders and you measure them each for 5 years, or 4 years I think I had said, then you get from 3rd grade to 9th grade in terms of your data, even though any one kid didn't give you that whole thing. So you're really hoping that you can sort of piece together these cohorts that start at different places, and that's a testable assumption that you can do that. If you're in a situation in which your cohorts all come from like the same school, the same time frame, the school hasn't changed anything they're doing, then yeah, it might be reasonable to expect that last year's 4th graders look like this year's 4th graders. As an alternative example, there's folks at Penn State who study things like victimization and bullying and things, and let's say that the school unveils this, hey, don't be a bully program, right, in the middle of one of your cohorts. Well, if it worked, last year's 4th graders shouldn't look like this year's 4th graders. And so that's going to screw up your design to the extent that these cohorts don't map onto each other. And so whether you think about cohort as a nuisance that you have to control for or whether you think about it as an effect that you care about is up to you. But in that case, because grade is both between and within, it has to have separate effects between from within. And whenever there is between-person variance in time, that between-person variance can capture random intercept variance of its own accord. Other questions? Okay, when did I say break was in the afternoon? Did you say it's on there somewhere? 2:30? Is that what I said? Man, I'm mean. Well, 2 o'clock then. It's not time yet. But if you do need to get up for a moment, please feel free. I won't be offended. So pseudo R square is that. Here's an alternative that I find myself turning to more often. It is a complementary source of information that almost always works. Total R square. I don't think I invented it, but I couldn't come up with a reference, and so I renamed it and called it my own, as one tends to do in the methodological field. So if you have your model calculate predicted outcomes for every single case in your data set, all software does this for you easily. It's a one-line option. You can take that correlation, the column of predicted outcomes from the fixed effects, correlate it with your real outcome column, that's R, you square that, and that's R squared. because questions about effect size for pseudo R Square are always for fixed effects, never for random effects. So you can generate a model prediction based on just the fixed effects and see how well it does in capturing variance as a whole. And that can give you sort of a put back together again version of effect size that goes across the levels of the model. So it's more general. It can be sort of unfair in models where there's huge sections of variance where you don't have any predictors, and so you never were going to get it, so your best R square is never going to look that good. But it does work in a lot of cases, and it can be easier for readers to understand who are used to seeing like regression models where there is only one square, R square. So long as you describe how you computed it, I think it's fair to call it total R square. So I will show you in the examples how to do both of these things, and I often would report both as a way of giving everybody what they want. But there is no one R square, so whenever you do use these things in papers, make sure you give the formula and the reference. Just describe how you computed it, and you can give a reference. And it would be lovely if it were my book, but it doesn't have to be, because other people do this too. All right. So then random. So this is C or D in the picture. This is the point at which we are allowing each person to have their own slope variant. Different flavors of linear, as it were, in this case. So everything is the same except for one letter. See if you can find it. We'll play Where's Waldo, equation style. What has changed? I'll give you a hint. It's in level 2. U. Which U? U1, there it is, right there. This is really the world of multi-level models. Everything else you could pass off as some other version, like repeated measures ANOVA. This is where the differentiation begins. There are no random slopes in ANOVA. So U1 is how far off from the fixed slope your random slope is. It's a deviation, where the mean is the fixed slope. In allowing each person to have their own slope, we have also added another parameter that doesn't show up in these equations but does show up in the model, which is a covariance between the U0 variance and the U1 variance. Because it stands to reason that if I have a U0 and I have a U1, they're probably related because they come from me. So the combined equation then shows how the beta 0 placeholders hold the fixed and the random, both with respect to the intercept and with respect to the linear time slope. So here's a picture that may help with this. So here's that combined equation from the same random linear time model. The black line in this picture is the sample mean, and the blue line is for me. And the triangles are my real data, and the diamonds are the real data for the sample means. So we're drawing trajectories through the means. We're trying to approximate the means with lines in this case. So note that time 0 is the first occasion. It doesn't have to be. It can be wherever you'd like. It's good if it's in your data, though. So as an example of what not to do, I once helped someone troubleshoot a model looking at older adults where everyone in the data set was 80 or older, and she forgot to center age. And her random intercept variance blew up and the model wouldn't estimate. And I said, well, you realize that you're estimating individual differences among newborns using these octogenarians, right? That's not necessarily wrong, but as you can imagine, it didn't go well. So time 0, best somewhere within the data you have. Doesn't have to be at the beginning. But here it's at the beginning for simplicity. So my fixed intercept here to start with, that's right here. So it's where the line ends up, not necessarily the first occasion. It's the predicted first occasion from the trajectory on average. Now I am starting out lower than everybody else here. So my U0 random intercept is going to be a -4. My predicted intercept, again, the end of my line, not the triangle, but where the line ends, is 4 lower than the fixed intercept. So if you put these together, my beta 0 for their combination would be the 6 that I actually have. Next, the fixed slope. Going back to 8th grade algebra, rise over run, delta y, delta x, remember all that? So the slope for the sample on average is 6. But I started out lower, so I'm growing faster. So my U1 is a +2 because my slope is 2 units more positive than the sample. So these two put together give me my beta 1, that's 8. And last but not least, because I have 3 or more occasions, my line does not fit my data perfectly. So E is how far off my line is from my actual observations. And if my model for time is complete enough, in theory, E should have constant variance over time and no covariance, because the only reasons why the E's would have been related are the U's that are already in the model. So I have built in now 2 kinds of person dependency. Observations from the same person are related, 1, because some people start out higher or lower than others. That translates into mean differences that predict some kind of constant dependency, but also there is a predictor-specific person dependency that is created by the fact that I change differently than others. And so that gives me another pattern of residual correlation that also makes the variances change over time. So each occasion has an E, each person has an E, and in these types of models, it's usually pretty reasonable to expect that residual variance is constant across persons and occasions. Okay. How are we doing? Question in the back. Good question. Sometimes there is a point at which there's an isomorphism between a random linear time model and an AR1 model if you only have 3 occasions. But generally speaking, yeah, the objective of these models should be to get as many reasons for residual covariance into the U's as possible, so that the model for the E's can be as simple as possible. If you only have 4 occasions, I would say, yeah, you should get to the point where your E's really don't have a residual covariance. If you have like 20 occasions, that may not be reasonable. So it may be the case that even after controlling for random effects of time, that the residuals that are closer together are more related, and that's where modeling like an autoregressive structure on the residuals specifically could be a reasonable thing to do. And that adds only one more parameter, because it's 1 unit apart is R, 2 units apart is R squared, 3 units apart is R cubed, and so forth. And that's the one that can work for unbalanced data as well. Whether or not you need that is another likelihood ratio test. Does the model fit better with it or without it? Others. So we talked about, you listened about, I keep saying that, the idea of significance versus effect size. So for fixed effects legitimately explain variance. So their significance is easy. You stare at the p-value. It's a Wald test. Fixed effects explain variance, so we can calculate pseudo R square or total R square to talk about effect size. For random effects, for significance, we do likelihood ratio tests. That tells us if the model fits better with it or does not change if we add it. So it's either better or not better as we add things. But that's not effect size. That's significance. And it can be challenging to convey in a more absolute sense how much variance you have other than just, well, it's significant. So there's a couple of strategies. one that I like that I did not invent, I stole this from Snyders and Bosker, is the idea of a random effect confidence interval. And this is not your mother's confidence interval. This is different. Normally, confidence intervals are about the precision of a fixed effect. Like if I did this study and over again in 95% of the samples, my fixed slope would be in this interval. That's not this. This is a way of tying the fixed and random effects back together again to talk about people. So for instance, if I have a fixed slope of 1.72, these are using numbers from the beginning of that y increases by 1.7 per unit time on average. I can get a significance test for that, stare at the p-value on the Wald test, and I can calculate a pseudo R square for the residual variance. I then have a test for whether or not the random linear slope is significant, and let's say that it was, and here's my estimate. So the variance of the U1s is 0.9, and I'm like, is that good? Is that a lot? Like, well, it's not 0, but not 0 means very different things in a sample of 20 versus 200 versus 2,000. So how much is it? Well, every effect in your model that is random also has a fixed effect with it that should be the center of its distribution. So let's put them back together again. A random effect confidence interval with 95% as the interval is the fixed effect plus or minus 1.96, that comes from the t-distribution, times, and I'm going to say this since I'm in Illinois, I believe I can say this, the square root. Is that acceptable? See, it's a Midwestern dialect thing. It is the square root. Am I right? Yes, I sit up on the roof, I drink root beer, and I calculate square roots. That is how I learned it. Some of my students cringe openly when I say that, and to them I say, fine, root. So whether this is the square root or the square root, should we take a vote? Rooters? So, they're like ashamed. Yeah, that's me. This is my heritage. I own it. Yes. I grew up with my mom who told me, you're not being Have. And to me that made complete sense, and it wasn't until I was an adult and I thought, what? She sat on the roof too and made her square roots. But so this is the square root? Is that the vote I'm hearing? It's the root? No? Oh yeah, the men in the back are like, you got that. Or is this another generational thing? Am I totally misrepresenting this? Maybe the students in my class don't like root because they were all born in this like millennium. Maybe that's the problem. Any insights into this? Historians, sociologists, linguists? No one? All right, fine. I'll make you happy. It is the root. But you do remember what the square root of a variance is, right, folks? What is it? Standard deviation, yeah. So what I'm doing is saying, hey, my middle is my fixed effect, and I'm going to go out about 2 standard deviations on either side to talk about what the effect is going to be across my people. So on average, my fixed effect is 1.7. That's how much the average person changes per unit time. If I plug these numbers into my formula, though, I get a range from minus 0.15 up to 3.59. So that is a prediction. It's not an actual, but it's a prediction that 95% of the people in my sample are predicted to have individual slopes ranging from basically 0 up to 3.5. So that's a way of quantifying in the scale of the original variables how much the variability around 1.7 really is. Does it predict variability such that some people actually decline and some people increase a whole lot? Because that's what this kind of looks like. And this is a point of confusion for reviewers frequently. So you will have to explain what these intervals mean, because they're going to look at this interval and go, hey, your slope's not significant. That interval crosses 0. And I would say, nope. The response to that letter would always be to start with, I'm sorry that my writing was not clear enough to convey this. Because when someone doesn't understand, it is your fault, always. As now hopefully made more clear on page 12, or whatever it is, this interval describes the range of slopes within my sample. The negative value indicates that some people are actually predicted to decrease, even though on average, people did increase significantly if this fixed slope is significant. So you have to tread carefully in how you word these, but I have found these to be effective in talking to people about what does this model mean. If I had a random slope variance that was significant, but my interval went from 1.70 to 1.74, I would be less interested in that. This can also help you phrase your discussion in terms of talking about individual differences in change as something like individual differences in growth, which would be what I would call something like this, where it's like 0 to positive, versus just individual differences in change if the middle was near 0 because some people went down and some people went up, versus individual differences in decline if it was a negative number and the interval was mostly negative. So it helps with the language, it can help with the interpretation. I like it, so I wanted to provide it for you as an option. Questions? All right. Okay, little bit of mathy stuff, because I want you to be able to find these things on your output. So how the piles work to put things back together again. This idea of making piles of variance, it's just a heuristic. That's not really what's going on. It's a way to build a complex pattern of variance and covariance that put back together again represents your data. So in a random intercept model, which is what we had to start with, I want to introduce you to some new letters. The place where the level 2 random effects variances and covariances are going to live is called the G matrix. That is what it is called in documentation in SAS and SPSS. If you're looking in other programs, you need to look at what, just look for random effects variances. It's RE level, I think, in Stata. Where's my Stata person? Somebody came to me. Yeah, there you are. Be proud. Yes, RE level something or another. Level 2, between person, random, G. Use. Level 2 random variance in the use. At level 1 is your R matrix. So this is residual. So this is what it looks like for 4 occasions after we factor out this random intercept and stick it over here in G. What's left has equal variance across time with no covariance. To put these two back together again, the combination of G and R put back together again is what's called V. And you can think of it as V for variance or V for victory. I finally understand this, because this is one of the things I had a hard time with for a very long time. If you're not a matrix algebra person, then I will give you this description. If you take this random intercept variance and just like stick it everywhere in here, you get this. That's what it looks like, right? If you're thinking, hey, you can't do that. I know. G gets pre and post multiplied by another matrix so that it's the right shape to add it to R to make it to V. And that other matrix is called Z, and it holds the predictors that have random effects. So for this person, all they have is a random intercept, so it's a column of 1s. We flip it sideways so that this becomes a 4x4 to add to this. And this V matrix then, if you compute the correlation version, that's where your ICC shows up. So level 2G is your between person random intercept variances and covariances. Level 1 R is your within person random or residual variances and covariances. Z is how you tell it what data you have that go with the random effects, just the intercept here, and V is everything put back together again. So because you can't straight add G plus R, I generally say G and R instead as sort of my shorthand for that, to which I also have to say, welcome to the jungle, folks. We got fun and games. We got everything you want. No? I just love dating myself. So here's what it looks like then once we add a random linear slope. Now we are putting in two kinds of dependency, two reasons why the residuals from the same person used to be related. One is because of the intercept, that's right here. And now another is because of person-specific differences in the effect of level 1 time. Random time slope, random slopes for different folks. So G is now 2 by 2. They get a covariance. By the way, this is not the default in any software package, which blows my mind. The default is to have no covariances among your intercepts and slopes, which makes no sense. Because why would the intercept and the slope from the same person not be related? But it's not the default. This is just a little piece of job security. I think if the people who make these packages make it hard, they keep themselves employed. That's my theory anyway. So now you can't just like take this intercept and like stick it everywhere. This doesn't quite work. So I'll show you how it works in just a second. So here's the derivation of what this model actually predicts. And in the book in Chapter 5, I walk you through it. But the big picture here that I want you to see is at the bottom. What the random linear time model says should happen to the variance is that the variance changes systematically, quadratically, over time. So here's the random intercept variance that we started with at level 2. Here's the level 1 residual variance that we started with. The new part is in blue here. By adding a random linear time slope at level 2 and its covariance at level 2 with the level 2 random intercept, we've picked up these extra terms that say that variance changes quadratically as a function of time. There's time squared sitting in there. So this is cool from the sense that we now have a heterogeneous variance model. Let me go back for a second here to show you this picture again. This unstructured matrix right here says that all the variances get to be different. But in this case, it took 4 variances and 6 covariances, or 10 parameters, to get that to happen. In the model that we are looking at, rather than spending 10, we are spending 4. Here we are. An intercept, a slope, a covariance, and a residual. 4 parameters instead of 10 that are now allowing the variance to differ over time. But it's differing as a function. It's not what is it at 1, what is it at 2, what is it at 3. It's a function that implies variance changes continuously across time. Now the reason that's so exciting is because of unbalanced time. What if you have time 1 1/2? There's a formula for you. What if you've got time 2 1/4? There's your formula. So it predicts variance across time for all the times because it's doing it as a quadratic function. So this model predicts that variance will be at a minimum at some point, and it will increase quadratically at either side of that minimum. It predicts that people spread out across time. That's what it does. And this works exceedingly well for data in which there are changes in variance across time in a single direction. The variance increases across time or it decreases across time because you're on one side of the parabola in that case. So it's changing it to a middle ground. It's like the baby bear of the story. Like mama bear is all the variance is the same, and daddy bear is all the variances are different, and this is like baby bear. It's like different, but different in a pattern that takes fewer parameters and allows us to generalize that pattern to in-between occasions. Maybe you're not as excited about this as I am, but like I just think that's so cool. Like, who came up with this, man? This is awesome. Not me. I'm just the translator. Same thing with the covariance. So here's the derivation of how we got here, but the big picture's at the bottom. With the random intercept only, we said the occasions were all equally related. Now we adjust that prediction of covariance between occasions to reflect which occasions it's the covariance for. So it's a function of time, which allows occasions that are closer together to have a stronger relationship than occasions that are further apart. And it can extrapolate across any occasions, not just the ones that we're supposed to have. Sir?
So the question about
unequal intervals or unbalanced? 'Cause unequal intervals but balanced?
Yeah.
Okay.
So for example, we actually have a study right now. We've got baseline to 4, 6, 8, 12, 7 days collection. And we're having these discussions about, okay, when should we stop collecting data from people because they're only spaced 2 time and the unit of time is 2 weeks.
Mm-hmm.
But if we collect somebody, then the outcome variable is subject. So if we collect somebody's follow-up a week late, then you have an overlapping interval.
Yep.
Well, you have overlapping time intervals, basically. So
Mm-hmm.
we're a little skittish about, I don't know that each of them, so what would you say about that in terms of, I know it sounds like each of them is great for, dealing with that, but then really it seems like you're creating another problem because you're actually, your two data points are actually covering the same period.
I think the solution is to think about it at the individual level. So if are you asking them like, how much drugs did you do in the last 2 weeks kind of thing? And so if they answer a week late, is it over the last 3 weeks, or have they shifted the interval to just be like they skipped a week completely and they're reporting on the last 2?
The questions are pretty static, so they always are about in the last 2 weeks, how many days did you use alcohol, how many days did you use drugs?
Okay, and why would they be late in completing the assessment? They were high, yeah. I believe we call that informative missingness, right? I think you can still put in like what time it was. Like I would if it was supposed to be week 8 and it's week 9 when they answered, make it week 9 in their data. Because you would expect. The other thing that you could do potentially is if you don't know whether or not they're referring to the last 3 weeks or the last 2. Is it like number of times you've done this, or how is it phrased? Number of days. So if I delay a week, then I have 21 possible days instead of 14. I could have done something, so I have a higher incidence. Can you do it like as a base rate then? Make a denominator with how long it's been, so that it's the same interval. Well, so if they did it at week 9 and week 10, then if you divided the week 9 observation by 21 and the week 10 observation by 7, would that help at all? Okay. Yeah, I don't know that that's because you have to trust their instruction. Like, are they skipping a week and really just doing 2, or are they like lumping things together? Because recall is a little sketchy even in people not doing drugs generally. I've been told. Today I'm a cognitive psychologist. So I think if you control for base rate, potentially that might help. But it depends on how accurate they're being with their recall. Like, are they really covering 3 weeks, or are they just covering the last 2? And unless you know that, I don't know how you would correct for that. If you're thinking that if it's more like as time goes on, they should be using less and less and less, is that sort of the idea?
No, I mean, usually there'll be an intervention, particularly if there will be a bigger intervention effect in the closer time. So
Mm-hmm. Like that? Okay. Like a stop kind of view, or they come back up? Asymptote down kind of thing? If you trust them that they're answering about just the 2 weeks, then that would, but it's time 9, so they should be further on that curve. You'd want to know that it's time 9. If you don't trust like the base period, then I would think you'd still want to call it time 9, but divide by the number of days it's been between each. The latter solves if you get them at 10, but you may just want to move them over. Like for the rest of the time, they're going to do 11, 13, something or another to try and recapture the 2-week interval. I don't know that there's a good answer to that, but those are the things that come to my head. So yeah, real data is never easy from real people who have a choice whether they cooperate. Okay. Other questions? She brought a blanket. She was thinking ahead. Well, on that note, I'm talking into our break. So how about we take 20 minutes, go unthaw, grab some caffeine, and we'll come back.